So let's look at this integral. The integral of x minus 2 over x, this pen is trash. X squared minus 4x minus 12 dx. Now, if we look at this one, we might immediately jump to the conclusion that we should do partial fractions. And I just want to remind you, this is an example of, even though we could do partial fractions here, right? The denominator totally factors as x minus 2 times x plus, or x plus 2 times x minus 6. Before you jump to partial fractions, you should ask yourself, can I do a u sub? So I'm going to try letting u equal the denominator, x squared minus 4x minus 12. And then du is going to equal, the derivative of that is 2x minus 4 dx. And I can see that if I factor out a 2 there, my du is equal to 2 times x minus 2 dx. So that 1/2 du is equal to x minus 2 times dx. And I exactly have that. So instead of doing integration by parts here, I really should just do a u substitution. So, okay, sorry, guys. So many people, myself included, I've heard students do a number of times, say integration by parts when they mean partial fractions because they both have the word like part in them. So we should not use partial fractions here because we can do a u sub. So we're going to say this is equal to 1/2 du. Then I have a 1 over u. And so the integral is going to be 1/2 natural log of the absolute value of u plus c, which is then 1/2 the natural log of the absolute value of x squared minus 4x minus 12. So if you can do a u substitution, then it's usually the better thing to do. Or maybe not, better is probably not the right word. It's the easier thing to do. This one you definitely could use partial fractions. If you use partial fractions, you would end up getting something like the natural log of x minus 6 plus the natural log of x plus 2, and then you could combine those together to get this same thing here because you combine it with multiplying inside. So you would get the same answer. It's going to be a more of a process. On the other hand, what if we had to integrate, say, I don't know, x minus 3 over x squared minus 4x minus 12? Well, now we can see that it's not going to work to do a u sub, right? The same choice for u is now not going to get us our numerator nicely. So here we are going to do partial fractions. So we're going to say x minus 3 over, well, actually, I should double check. We can factor this. Yes, the factor is x minus 6 times x plus 2. That's going to equal a over x minus 6 plus b over x plus 2. There's no specific way of choosing which order to do this. Any order is fine. I just kind of pick whichever factor I see first. So then, the reason I'm doing this one today, I want to remind you all that it's a good idea to start all two of you. I want to remind all two of you and people watching this later that it's really good to start with this so that you can see what you're doing in the next step. The next step is just to multiply both sides by your common denominator. The whole point of doing this is so that you end up with no more denominators. And when you multiply x minus 6 times x plus 2 by the first thing over here, you're just going to get x minus 3. When you multiply it by this piece here, the x minus 6's cancel, and you get a times x plus 2. When you multiply it here, the x plus 2's cancel, and you get b times x minus 6. And what I want to show you here is actually two ways of doing this. So I'm going to show you my way, the way which we've been doing in class, which I think is the better way. But I also want to point out your teachers might have shown you a different way, which is equally valid. It just feels like more work. So here's one method of solving this. Pick nice values of x, meaning pick values of x that make things 0. So I'm going to pick the value of x that makes this part 0. So I'm going to pick x equal to -2. If I plug in x equal to -2, I'm going to get -2 minus 3 on the left equal to a times 0 plus b times -2 minus 6 is -8. Solving for b, I'm going to get -5 over -8, so b is going to equal 5/8. And then the other convenient value is going to be x equal to what? All right, there's only one of you in the chat, so type it in the chat. What should, I already wrote it. Sorry, like your brain just sometimes like, oh yeah, x equal to what? Let me just write the answer. Sorry, it's too late. I already told them the answer. So we plug in x equal to 6. 6 minus 3 is 3. A times 6 plus 2 is 8. and b times 6 minus 6 would be 0. So we're going to get a equal to 3 divided by 8. Alternatively, your teachers might have shown you this other method called equating coefficients or grouping terms and seeing same things. So we could say we have x minus 3 equal to, if I multiply this out, I have ax plus 2a plus bx minus 6b. And if I group like terms, I have a plus b times x. And then my constant term is 2a minus 6b. And then they might do this thing when they say, okay, well, a plus b equals x. Sorry, a plus b equals 1, apologies, because the coefficient here has to equal the coefficient there. And 2a minus 6b equals negative 3. This is more work, right? This definitely takes more effort to do. It will get you there. I would probably then solve this. So I don't really want to finish this because it's kind of, I should finish. I started it, I should finish it. So if I substitute in a equal to 1 minus b, so right, this is going to give me a equal to 1 minus b. We can plug that in over here and then say, okay, 2 times 1 minus b minus 6b equals negative 3. Sorry, I'm in the section that you can't see. 1 second. It's always the hard part of doing it this way. Okay, so then 2 minus 2b minus 6b equals negative 3. Negative 8b equals negative 3 minus 2, which is negative 5. And then b equals 5/8. And then a equals 1 minus b. So a equals 1 minus 5/8, which is 3/8. So you do get the same values. It's just more work. So what I would encourage you to do is to not do it this way, but to do it this way. And then we'll talk more about doing this when you are done with this. Rewriting this integral, this is going to equal the integral of a, which is 3/8 over x minus 6 plus b, which is 5/8 over x plus 2. And then most of the rest of this becomes pretty straightforward. 3/8 times 1 over x minus 6, the integral is 3/8 times the natural log of the absolute value of x minus 6, plus the integral of this is going to be 5/8 times the natural log of the absolute value of x plus 2, plus c. You might see people combine this or condense this into one logarithm. I wouldn't really do that unless they happen to have the same coefficient. Here, you could write this as the natural log of x minus 6 to the 3/8 power plus the natural log of x plus 2 to the 5/8 power, and then smash those together, but there's no good reason to do that. Let's look at a few more examples. Actually, let's look at a really gnarly example. This one's actually from the homework assignment, my version of the homework assignment anyway. Welcome. Thank you. So let's look at, this is problem 9 from Burke's current homework assignment, at least my version of it. The integral of, let's do 9 and 10. At least, we'll start with 9. Actually, I really want to do 10. Let's do 10. 10's even grosser. So this is going to be a bit much. So here's my numerator: 4x to the 4th plus 18x cubed plus 30x squared plus 29x plus 12 divided by. Oh, darn it! I did the thing where sorry, that's not the right thing. My eyes got distracted and I looked at the wrong thing. Okay, let's try this again. The integral of 4x to the 6th plus 18x to the 5th plus 28x to the 4th plus 31x cubed plus 44x squared plus 32x plus 16. Wow. Divided by x to the 4th plus 4x cubed plus 4x squared. Okay, here's the good thing about this problem. Probably. When they're as gross as this, usually it means someone has actually taken the time to make sure that the numbers turn out not terrible. So, u substitution is off the table, because if I let u equal the denominator, the derivative is going to be something x to the 3rd, and I have a much higher power. So that's not even a good choice. Can I do partial fractions here? Do I meet all the requirements? Is it a rational function? Yes. Is the denominator factorable? For sure, right? We can definitely factor out an x squared and probably some other stuff. Is the degree on top less than the degree on the bottom? It's not. So before we can think about partial fractions, we first have to do polynomial division. If the degree on top is greater than or equal to the degree on the bottom, we have to do polynomial division. Which is kind of a lot here. It's okay, it's going to work out. So we have x to the fourth plus 4x cubed plus 4x squared going into this giant thing here, 4x to the sixth plus 18x to the fifth plus 28x to the fourth plus 31x cubed plus 44x squared plus 32x plus 16. Honestly, half the battle with this problem is just making sure you write down things correctly, right? Making sure you don't accidentally write the wrong thing. So let's see. So when you multiply by x to the fourth to get 4x to the sixth, it's going to be exactly 4x squared. And then we multiply by everything. So you get 4x to the sixth plus 4x squared times 4x cubed is 16x to the fifth. 4x squared times 4x squared is 16x to the fourth. Subtract. Welcome to those of you who just came in. We're doing a long partial fractions problem. And first, we have to do this polynomial division. So that minus that's 0. 18x to the fifth minus 16x to the fifth is 2x to the fifth. 20x to the fourth minus 16x to the fourth is 12x to the fourth. Bring down the next term. And then we do it again. X to the fourth times a 2x will get me a 2x to the fifth. So then I multiply 2x by everything. I get 2x to the fifth. I get 2x times 4x cubed is 8x to the fourth. 2x times 2x times 4x squared is 8x cubed. Subtract. So 12x to the fourth minus 8x to the fourth is 4x to the fourth. 31x cubed plus minus 8x cubed is 23x cubed. Bring down the next term. So then, when you multiply x to the fourth to get 4x to the fourth, it's going to be a 4. So then 4 times that is 4x to the fourth, plus 4 times that is 16x cubed, plus 4 times that is 16x squared. Subtract. 0, 23 minus 16 is 7x cubed. 44 minus 16 is 28. Yeah, 28. All right, and then we stop because you can't, right? I'm not going to bring down more terms because you can't like put x to the fourth into the 7x cubed. So this tells me that I can rewrite this integral as the integral of this quotient, 4x squared plus 2x plus 4, plus the remainder, which, okay, I guess you could bring down the last two things to see what the remainder is. The remainder is going to be 7x cubed plus 28x squared plus 32x plus 16. Divided by this denominator, x to the fourth plus 4x cubed plus 4x squared. Something to be aware of. When you get to this point in your, like, so if you say you've done polynomial division, you should definitely check at this point if you can now do a u sub for your new fraction. It's not going to work to do a u sub here, right? If we let u equal the denominator, du is going to be 4x cubed plus 12x squared plus 8x. That's definitely not going to work nicely with this, but sometimes it works out perfectly. So definitely, after you do polynomial division, it's a good idea to check to see if your new rational function can be done with a u sub. This one can't, but it's worth thinking about. So now we're going to do the partial fraction decomposition. So we're going to say, all right, 7x cubed plus 28x squared plus 32x plus 16 divided by, we want to factor this. If we factor out an x squared, we're left with x squared plus 4x plus 4. And x squared plus 4x plus 4 factors as x plus 2 times x plus 2. Now, I really don't want to write it as x plus 2 times x plus 2. I want to write it as x plus 2 squared. It is really important that any factor that's like occurs repeatedly, you write it as that thing to its highest power. You don't want to write it as x plus 2 times x plus 2. And then let me ask everybody. I want you two to show me on your hands, people on Zoom to type it in the chat. How many pieces, how many fractions is my partial fraction decomposition going to have? I was on fingers.
I just have a question.
Sure.
Where did 4x squared plus 2x plus 4 go?
So say that one more time.
Where did 4x squared plus 2x plus 4
So it's still there. So right, notice that I didn't write the integral here.
Oh,
Right, I'm just dealing with
okay.
this piece here. But I'm gonna come. So what I'm eventually gonna do is I'm gonna writing this as the integral of 4x squared plus 2x plus 4 plus something over x plus something over x squared and so on and so on and so on. So I'm not even done writing the integral yet. So for those of you at home, the number of pieces are going to be, yeah, exactly. Thank you. 4. We're going to have a over, I usually like to do it as the powers get larger, but you can write it anyway. So I'm going to have something over x squared and then every lower power. I usually write it as a over x and then b over x squared. But any way of doing it is perfectly fine. And then similarly, for the x plus 2 squared, I have to have every lower power as well. So I'm going to have a c over x plus 2 and a d over x plus 2 squared. And we're going to multiply everything by the denominator. So when I multiply everything by x squared times x plus 2 squared, the left side, you just get the numerator. So we're going to have 7x cubed plus 28x squared plus 32x plus 16 equal to, all right, when I multiply this by a, one of the x's cancels and I get a times x plus 2 squared. I'm going to get b times x plus 2 squared because the x squareds cancel. I get c times x squared times one of the x plus 2's, and I get d times just x squared. And then we start using convenient values, right? You definitely, equating all those coefficients here definitely is a very challenging process, whereas using convenient values of x, like x equal to 0, can be nice, because if I plug in 0, I get 0 plus 0 plus 0 plus 16 equal to, if I plug in 0, I'm going to get 0 there, I'm going to get 0 there, and I'm going to get 0 there. The only place I'm not going to get 0 is the b term. So I'm going to get b times 0 plus 2 squared. That's b times 4. So 4b equals 16. So b is equal to 16 divided by 4, which is 4. If you have questions, don't hesitate to ask them. So let me ask you all, what's the other nice value of x I can pick to plug into this for this equation? Right, definitely going to be -2, because -2 is going to make a lot of things 0. So if we plug in x equal to -2, so now we have to be a little bit more careful, because plugging -2 on the left side actually requires doing some math, right? Some arithmetic. So plugging -2, I'm going to 7 times -8 plus 28 times -4, sorry, +4, plus 32 times -2 plus 16 equal to 0 plus 0 plus 0 plus d times -2 squared. Okay, simplifying this, 7 times -8 is -56. 28 times 4 is 28 times 2 is 56. Times another 2 is 112. This would probably be a good time to use a calculator. -64 plus 16 equals 4 times d. So then -56 plus 112 is 56. 56 minus 64 is -8. Plus 16 is +8. So I get 8 equal to 4d. So 2 is equal to d. Okay, but now we've run out of convenient values of x. There are no other good choices for x that are going to make lots of things 0. So there's a couple of different ways to go here. One way is to just pick other values. You could totally pick x equal to 1, but if you and plug in like what your b and your d values are. But the problem is we still have to find a and c. So we're going to end up getting equations with multiple things left in them. Here's what I would recommend doing at this point. What I recommend doing is now equating coefficients. So if I look at both sides of this equation, I always ask it this way. What's the highest power of x on either side? In this case, it's x to the third. So I'm going to look at the coefficient of x to the third on each side. So what's the coefficient of x to the third? Well, on the left side, that's easy. It's 7. On the right side, if I multiplied it out, so let me ask everybody, if I multiplied out this first term, would I have an x cubed? If I multiplied out x times x plus 2 squared, I definitely would. And the coefficient would be a. Because here's the thing, I'm trying to save, like, I don't want to write it all out, but I just want to point out, if we multiply this out, we would have a times x plus 2 squared is x squared plus 4x plus 4. So I'd have x cubed plus 4x squared plus 4x. And if I multiplied the a to each of those, I'd have an ax cubed plus 4ax squared plus 4ax. So the coefficient of x cubed is definitely a. In a similar way, well, actually, I don't have any x cubed here. I do have an x cubed if I multiply this out, right? This would be a c times x cubed plus 2x squared. So I definitely have a c times x cubed. And of course, we happen to have picked the thing where it's actually, we don't have either of those values yet. We have b equal to 4 and we have d equal to 2, but we don't have a or c. So we actually need to do more, which is not surprising because we know we had two things left to find. So I was pretty sure we're going to need two equations anyway. So let's table that for a second and now look at the coefficient of x squared. I do recommend going from highest to lowest because usually the higher powers have less terms involved with them, so it's easier to solve for things. So looking at the coefficient of x squared, on the left side, the coefficient of x squared is 28. On the right side, let's see. If I multiply out this first term, I'm going to get a 4a times x squared. People often kind of miss the 4 there and just say they have an a times x squared, but there is a 4 times a times x squared if I multiply that out. If I multiply out this one, I get a b times x squared. If I multiply out this one, I get a c times 2 times x squared. If I multiply out this one, well, there's nothing to multiply out there, I get a d times x squared. So now we have enough because we know that b is equal to 4 and d is equal to 2. So now we can say, all right, we can say 28 equals 4a plus 2c plus 6. And then I can solve one of these for a or c. So I can say, all right, c equals 7 minus a. And then I'm going to plug that in right there. So 28 equals 4a plus 2 times 7 minus a plus 6. So 28 equals 4a plus 14 minus 2a plus 6. So 28 equals 4 minus 2 is 2a plus 14 plus 6 is 20. So 8 equals 2a. So 4 is equal to a. And then 4 is equal to a. C equals 7 minus a, so c equals 3. All right, so now finally, we can write out our integral. So then we can say, all right, this integral is going to be the integral of 4x squared plus 2x plus 4 plus a over x plus b, where'd b go? B is 4 over x squared plus c over x plus 2 plus d, which was 2 over x plus 2 squared. Wow, it's a lot. And then we integrate each thing. So it's funny, the thing about these problems is usually the integration part is not the hard part. It's the making it look like something we can integrate. So then this is going to be equal to 4x cubed over 3 plus 2x squared over 2, which is just x squared, plus 4x plus 4 natural log of the absolute value of x, plus, be careful, I would encourage everyone to think of this as 4 times x to the negative second. So the integral is going to be 4x to the negative first over negative 1 plus 3 times the natural log of the absolute value of x plus 2 plus, same idea. Here, I would really encourage everyone to think of this. This is 2 times x plus 2 to the negative second, and the antiderivative of that is going to be 2 times x plus 2 to the negative first over negative 1. And if you really wanted to make it look a little bit nicer, you could write it as 4/3 x cubed plus x squared plus 4x plus 4 natural log of the absolute value of x minus 4 over x plus 3 natural log of the absolute value of x plus 2 minus 2 over x plus 2. Let's see. It's a beast, but very doable. It just, I mean, it's just going to take, right, as with a lot of things in math, it just takes time. Let's look at a couple more things. Yeah. Go ahead. Yes. It's not the only way. So that's a good question. Let's go back and revisit that.
But is this one the easiest one?
I think this is the easiest one.
Okay.
Right. So let's kind of, so here's what I will say. So looking back at this for a second, let's actually write this down again. So we had this equation. Now, the hard part really comes from when you have repeated factors. So, right, when we were trying to solve this for A, B, C, and D, right, here's what I will say. You always want to, sorry, 1 second here. It's not, it feels a little blurry. I'm sure I can. I can make it look worse. Okay. All right. There we go. So you always should do the first two things I did, right? Definitely. You always want to use what I call convenient values of x. That is surefire the fastest way to get things done to start. So I definitely want to let x equal 0 and get 0 plus 0 plus 0 plus 16 equal to 0 plus b times 4 plus 0 plus 0 to get me b equal to 4. Similarly, I definitely want to let x equal to -2 so I can get, all right, let's make this a little easier. So 7 times 8, -8 is -56. 28 times 4 is, sorry, 28 times 4, yeah, is 112. 32 times -2 is -64. 16, great. Equals 0 plus 0 plus 0 plus d times 4. And so this is a little bit messy, but not terrible. This is 56. -64 plus 16 is -48. 58, 6 minus 48 is going to be 8. So you end up with 8 equal to 4d, so d equal to 2. But then you do have choices. So you could do what we did, right? You could also pick other coefficients, right? You could look at lower ones like x, or, well, actually, we can't look at the constant term because we've already done that. Because when you set x equal to 0, you're essentially saying the constant on this side is equal to the constant on that side. So looking at the constant term isn't going to get us anything new here. Or you could just pick other values of x. So another option, instead of doing what we did, is to do the following. So pick easy values of x to plug in. Since things are kind of big here, you usually want to pick the smallest values of x that are easy. So I would pick like x equal to 1. So pick x equal to 1, I get 7 plus 28 plus 32 plus 16 equal to, now you're going to plug in your known values of b and d. So I'm going to get a times 1 times 3 squared, so a times 9, plus b, which is 4 times 1 plus 2 squared, so that's also going to be 9, plus c times 1 times 3, plus d, which we know is 2 times 1 squared. And then if we work with this, let's see. So 28 plus 32 is 60. 60 plus 16 is 76. Plus 7 is 83, equal to 9a plus 36 plus 3c plus 2. So isolating the a and the c, I would say I have, let's see, 83 minus 36 is 53 minus 6, which is 47. I have a 45 equal to 9a plus 3c. I think that's right. Yeah, 37. I think that might not quite be right. Let me double check. 81 minus, no, that's right. 81 minus 36. Yeah. And then we would pick another value of x. So any other number, I would probably pick -1. I'm trying to pick the things that are smallest so the numbers are not big. But literally, totally, yes, that's a good call. So then I should definitely say 15 equals 3a plus c. Good observation there. Yeah. And then we're going to pick x equal to -1, do the same sort of thing. So x equal to -1, I mean, you get -7 plus 28. Yes, because it's going to make things still small. I want things to be really as small as possible when I'm doing this. Just, I mean, really, you could pick 5 or you could pick 10, but I feel like it's just going to make things gross, right? So plus 32, oh, sorry, minus 32 plus 16 equal to, now I'm going to get a times -1 times 1 squared. So I'm going to get -a. I'm going to get b, which again is 4, times -1 plus 2 is 1 squared, is still 1. Great. And I'm going to get c times -1 squared times 1. So I'm going to get c times 1. And I'm going to get d times 1, but d is 2. So simplifying this, I have, let's see, -7 plus 28 is, well, let's do it this way. So I've got 21 there. I've got -32 plus 16, it's -16. So I have 5 on the left equal to 6 plus c minus a. And then I could solve one of these for one of them. So I can say, I don't know, -1 plus a is equal to c. And then plug that in up here. So then I'm going to have, all right, 15 equal to 3a plus -1 plus a. So then adding 1 over here, I've got 16 equal to 3a plus a is 4a. So 4 is equal to a. And then back to solving for c, c is -1 plus a. So c is -1 plus 4, which is 3. Is that easier? I don't think so, but you might. So any way is fine. You should try and do what works best for you. But yeah, when you have these repeated factors, right? When you have these, right, something squared, and you get each of the lower powers of it, that's when you're going to run into this thing where you run out of convenient values of x, and so you have to then do something else after that. But again, I would strongly emphasize you definitely should start with just using the convenient values of x. So a couple more, and then we'll start talking about improper integrals. So let's say I wanted to do this one, the integral of x over x squared minus 10x plus 25. So before I do anything, well, not before I do anything, I should, so letting u equal the denominator is not going to work, right? Because if u is x squared minus 10x plus 25, my du is 2x minus 10, which I definitely don't have. But if I start looking about how this factors, the denominator factors exactly as x minus 5 quantity squared. And I could use partial fractions here, but they could also do a u sub with a back sub. So one option here is u sub with back sub. We would let u equal x minus 5. Our du would equal dx, and then solving this for x equals u plus 5. So we can rewrite the integral as u plus 5 over u squared du. And then we could simplify this as u over u squared plus 5 over u squared du, which becomes the integral of 1 over u plus 5u to the -2nd. And then we can just anti-differentiate that. We get natural log of the opposite value of u plus 5u to the -1 over -1. And then plugging back in u equal to x minus 5, I get the natural log of the opposite value of x minus 5. I get minus 5 over u, or minus 5 over x minus 5 plus c. Or you could do partial fractions. In fact, I think it's worth seeing that both work. So doing it with partial fractions, we would say, okay, x over x minus 5 squared is equal to, this one is kind of weird. It's a over x minus 5 plus b over x minus 5 squared. It's not immediately obvious what a and b are, right? We don't just know that b, well, you can't say b is equal to x, right? A and b have to be constants. So multiplying it out, we're going to get x on the left equal to a times x minus 5 plus b. Now this one's not too terrible. If I set x equal to 5, I'm going to get 5 equal to a times 0 plus b. Great. And then pick any other value of x you want. I would probably pick 0. If I haven't already used 0, I would use 0. So picking x equal to 0, I'm going to get 0 equal to a times negative 5 plus b. So it looks like a has to be 1. So then I can rewrite this integral as the integral of 1 over x minus 5 plus 5 over x minus 5 squared. That's going to end up being the natural log of the absolute value of x minus 5 plus the integral of 5 over x minus 5 squared is, right, that's 5 times x minus 5 to the minus 2. That's going to be 5 times x minus 5 to the minus 1 over minus 1, which is exactly the same thing we got up here. I just written it slightly differently. So it really does work either way. Sometimes if you do integrals using different methods, you get answers that differ by a constant sometimes. In this case, we don't. They are literally the same through and through, which is fine. Let's look at how much time we got. Yeah, let's look at 2 more and then we will start talking about improper integrals. So let's look at this one, the integral. It's time to buy some more pens. The integral of x squared minus 4 over x squared minus 1. So let's see. Can I do partial fractions? Not yet. I have to do the division first. So that's an easy one-step division. X squared goes into x squared 1 time. So 1 times x squared minus 1 is x squared minus 1. We subtract. X squared minus x squared is 0. Negative 4 minus negative 1 is negative 4 plus 1, which is negative 3. So I'm going to rewrite this as the integral of 1 plus negative 3 over x squared minus 1. Or as I would probably actually write it, 1 minus 3 over x squared minus 1, which I'm going to factor as x minus 1 times x plus 1. And then we're going to do partial fractions for that. All right, I want you to both do it. You all of you both in class and on Zoom. You should do this partial fraction decomposition. It's good practice. So we should be getting a 1/2 and a -1/2, I think, for A and B. I don't remember which one's which, so let's find out. Or maybe a 3/2. I forgot about the 3. I guess I could have factored out the 3, but it didn't want to. So let's see. If I multiply both sides by that, I'm going to get 3 equal to A times X plus 1 plus B times X minus 1. And then setting X equal to -1, I get 3 equal to B times -1 minus 1. So B equals -3/2. And then setting X equal to +1, I get 3 equal to A times 2. So A equals +3/2. Yeah, sorry, not 1/2 and -1/2, 3/2 and -3/2. So then we can rewrite this integral as the integral of 1 minus, that's why it's not good to do that. All right, that's fine. So let's write this in the following way and kind of see what here's why maybe bringing up this minus sign is not the best way to do this, but let's see. So I'm going to write this as the integral of 1 dx minus the integral of 3 over x minus 1 times x plus 1. And I can rewrite that as, well, that's going to be x minus the integral of this is the integral of a, so 3/2 over x minus 1 plus b, which is -3/2 over x plus 1. But I feel like I kind of shot myself in the foot a little bit here when I wrote it like this, because I was kind of thinking about just this piece here. And I really didn't want to have to like write those in and then distribute the minus sign. So I was trying to just be careful. So really the name of the game is just be careful, right? It probably might have been better to do the following. To say, oh, this is the integral of 1 is x. This is x minus 3 times the integral of 1 over x minus 1 times x plus 1. Probably would have been better to do that first and then do the partial fraction decomposition for that instead. It's not a whole lot different. It's just slightly better. Anyway, doing it this way, we're going to get x minus 3/2. Oh, wow. Apologies. We're going to get x minus 3/2 natural log of the opposite value of x minus 1. And then we're going to get minus, so plus 3/2 natural log of the opposite value of x plus 1. Let's see. Okay, do one more and then improper integrals. And let's look at this one. It's the integral. Where'd you go? Yeah. X cubed over x squared minus 4. I should point out, it's not a huge deal, but there are 2 other types of rational functions that we do partial fractions for. But they don't typically get covered in 16B. So just be aware that no one should ask you about any other types of partial fraction problems in future classes, but there are other things that can happen in partial fractions, which are funky. But unless I see it coming up in your homework or on a practice test or something, I'm not going to show you the thing you don't have to know for your class, unless you really want me to, but I don't think you really want me to. So, another one where I have to do this division stuff. Okay, x cubed divided by x squared minus 4. You don't have to, but you certainly can when you do this. People like to write the rest of the terms so that they don't like forget about where a thing goes. It's also not completely necessary, but it's fine. I'm gonna multiply x squared by x to get x cubed. So I'm gonna get x cubed minus 4x. So I probably didn't put that in the right spot. It's okay since everything is 0. X cubed minus x cubed is 0, and nothing minus 4x is just a positive 4x. And then I'm done, right? There's no more division to do. So this is equal to the integral of x plus 4x over x squared minus 4. And this is kind of the situation I was talking about before, where while we could do partial fractions here, this new fraction is one where I can just do a u substitution. So I'm going to rewrite this as, I'm actually going to do the integral of this because I've got x squared over 2 plus the integral of 4x over x squared minus 4. we can do a u sub, letting u equal the denominator. Du is going to be 2x dx, so 2 du is going to be 4x dx. So I can rewrite this as x squared over 2 plus the integral of 2 du over u. And the integral of 2 over u is 2 natural log of the absolute value of u. And then that's going to be 2 natural log of the absolute value of x squared minus 4.
You also do it with partial function.
Partial fractions.
That's
Yeah, so typically I usually describe partial fractions as a method of last resort, meaning I would really like to do almost anything else first, just because usually the algebra for partial fractions just starts to get ugly. So yes, there are lots of things we can do partial fractions for, but we instead do a u sub if we can. But ultimately, whatever method works. So if you wanted to do partial fractions here, or if someone specifically said on an exam, do this problem using partial fractions, then you should do using partial fractions. But usually if we can do something else with an easier method, we try to. Okay, let's talk about improper integrals. So first of all, what makes an integral improper? Well, there's actually two varieties of improper integrals. The first variety we're going to talk about are ones where, well, first of all, I should say an improper integral is always a definite integral, right? You can't be an indefinite integral and be improper. So improper integrals are always definite. And the first type is the type where one or both of your limits of integration is infinity. So here is kind of the usual, if your teacher has talked about this in class, they've probably already done this example. It's still worth doing. The classic example is the integral from 1 to infinity of 1 over x dx. And I'm actually going to do this the wrong way first. It's not super wrong, but I'll say this is the way that people start doing it. It's the lazy wrong way. So this is going to not get you full credit on an exam, probably. What's the antiderivative of 1 over x? Yeah, well, actually natural log of absolute value of x. We don't technically need the absolute value here since everything is positive, but it's still good to be right in the right thing. From 1 to infinity, and then I'm going to get the natural log of infinity minus the natural log of 1. The natural log of 1 is 0, and the natural log of infinity is infinity. Now, the reason this is wrong, or not 100% correct, is this is not, you can go away too. This is not the proper way to evaluate an improper integral. And the reason it's not proper is because we're treating infinity like a number, and it's not a number. I want to make that really clear. Infinity is not a number. It's an idea, it's a direction, it's saying things are getting really, really large, but it's not a number. So this is not the proper way to evaluate an improper integral because we treated infinity like a real number. It's not super problematic in this particular example, right? Treating infinity like a number here totally works out fine, but it's just not the way we do things. So let me show you the proper way of doing it. Here's the correct, proper way of doing an improper integral. So whenever you have an integral with a limit of integration that is what I like to call problematic. So a problematic limit of integration is either infinity, like we're seeing here, or later on, if we were doing this, 0 would also be a problematic limit of integration because the function that we're integrating is undefined at 0. So anything that makes your integrand either undefined or infinity, or infinity just in general, those are your problem points that you have to replace. So we're going to rewrite this as, I'm going to replace infinity with whatever letter of the alphabet you like, except for x, not x, we've already using x. Typically, you replace an upper limit with b, a lower limit with a, but I see people use t or z or really anything. So I'm going to write this as the integral from 1 to b of 1 over x dx. But then I'm going to take the limit as b approaches infinity. So that's the whole idea. You replace your problem point with a variable name like b, and then you take the limit as b approaches whatever that thing is. And then we're just going to act like this is normal. So I'm just going to kind of ignore the limit until the very end. So I'm saying, okay, I know there's a limit out there. Yes, you have to keep writing the limit. If you don't write the limit, it's not the same thing, right? Those are not equal to each other.
Well, I mean, can we just write it at the end, like when we get the integral?
So I know what you're asking. I will do it that way in the next problem. I'll show you another way you could do it for sure. Yes, the answer is yes, but to be careful. And again, on your homework, right, that no one is looking at, you could totally kind of be loosey-goosey, but on an exam, I imagine someone's going to want you to write it the correct way. Probably, maybe not. So if we integrate 1 over x, what do we get? We get the natural log of the absolute value of x, evaluated from 1 to b. And then that's going to equal still the limit out in front. The natural log of x from b to 1 was the natural log of b minus the natural log of 1. I'm not writing the absolute values anymore because b is positive and 1 is positive. So I don't need to write the absolute value. Or more specifically, the absolute value of 1 is 1. The absolute value of b, which is a positive number, is b. And now I evaluate the limit. As b goes to infinity, what happens to the natural log of b? Well, if I think about the graph of the natural log, right, it looks like this. As x, or as the inputs go to infinity, the outputs also get infinitely large. This is going to be infinity minus 0, which is infinity. So when the integral is infinitely large or negatively infinitely large, we say that the integral diverges. And sometimes people will ask how it diverges. So if someone asks, we would say this integral diverges to infinity. It diverges in a way that it gets infinitely large. So it's kind of interesting, actually, that the area under the curve 1 over x, I'll try and draw here. So if we look at this curve, right? Obviously not perfect, but if you look at the area under the curve, that area, which doesn't look like a whole lot, as you keep going out further and further and further and further and further, the area under the curve grows without bound, right? There is no upper limit to it. It just gets bigger and bigger and bigger and bigger and bigger. It's kind of interesting. That's great. Okay, but now let's look at another example, and we'll do this one the way you were kind of asking about. Oh, question. Why is natural log 1, 0? Good question. Let me ask you a question in response. Here's my favorite one. What's log base 2 of 8? Right, because 2 to the third is equal to 8. So the natural log of 1 is equal to 0 because what's the base for the natural log? Right, because e to the 0 is equal to 1. So the question we're asking, right, when I write log base 2 of 8 or natural log of 1 or log base 3 of 81, we're asking this base raised to what power is equal to that number? So in this case, 3 to the 4th is equal to 81. In this case here, e, the only power of e that's going to get you to 1 is e to the 0th power. And it's actually true that whatever your base is, log of 1 is always 0. So if I said, log base 4 of 1, the answer is 0 because 4 raised to the 0th power is equal to 1. Does that make things clear? Then that's not very nice. So natural log of 5 is approximately something. It's between 1 and 2. I don't know, actually. If I got on my calculator, I would say, calculator time. My phone is over here too. The natural log of 5 is about, let's see. Sure. Where is my natural log button? I don't know about this. That seems not right. Yeah. Where are you, natural log button? How does the calculator not have an obvious natural log button? That's terrible. Really? I'm really like surprised that this calculator does not have an easy to find. It's got a log base 10 button. Who wants that? Well, fine then, I guess. Where put my phone? That's weird. So we'll use the phone calculator. Okay, let's see. It's natural log of 5. So 5 natural log there. It's about 1.609. But again, that's just an approximation, right? The only thing you can say natural log of 5 is actually equal to is natural log of 5, which I know is not very reassuring, but this is because e to the 1.609 is approximately 5. Right? That's the reason. It would still diverge because infinity, so infinity is infinitely large, right? It's really, really big. Anything that's infinitely large, if you subtract off a finite number, is still going to be infinitely large. Fair question though. So right, so if I had done this problem, so technically we could observe that you could actually start anywhere, right? I could do the integral from 5 to infinity, or from 1,000,000 to infinity, or from 1,000,000,000 to infinity, and still get divergence because I would still end up getting an infinity minus the natural log of some finite number, which will be a finite number. You're actually asking a very astute question, which is that when we do this divergence, convergence stuff, basically infinity beats anything else, right? If something's infinitely large, you can't add or subtract a finite number to it to make it not infinitely large. Yeah, so let's look at another example. This is kind of the second part of the classic intro to this, which is let's look at the integral from 1 to infinity of 1 over x squared dx, which I would first start off by writing as the limit as b goes to infinity of the integral from 1 to b of 1 over x squared. But now let's do it this other way. Let's say, okay, well, I'll come back to that. Let's just do the integral of 1 over x squared really quickly. It's not going to be natural log of x. And, well, it is going to be negative, but not natural log. So if we rewrite this, we have x to the negative 2. And what's the antiderivative of x to the negative 2? X to the negative 1 over negative 1, which I would prefer to write as negative 1 over x. So more to the point, if you have an integral and you don't want to write the limits and the limits of integration the whole way through, you can totally go do the indefinite integral off to the side and then go back and be like, okay, this is going to equal the limit as b goes to infinity of, well, now I know the integral of 1 over x squared is negative 1 over x from 1 to b. And then we can do the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. And as b goes to infinity, what happens to negative 1 over b? Does it get really, really big or really, really small? Let's see, 1 divided by 100, it's like 0.0.
There it goes to 0.
It goes to 0, right? When you have something that's getting divided by a larger and larger and larger number, that fraction is getting smaller and smaller and smaller. So this is going to end up being 0 minus minus 1, which is just 1. So this integral from 1 to infinity of 1 over x squared dx, we would say converges. And when something converges, we usually like to say what it converges to. It converges to 1. So if your improper integral has a finite value, we say it converges to that finite value. If your improper integral is some sort of infinity, positive or negative, we say it diverges. And we usually don't say what it diverges to because sometimes we can't, but occasionally in some classes, I feel like more in the 21 series than in the 16 series, I've seen web work questions where they specifically ask, tell me what this like if this interval diverges, say that it diverges to infinity, or if it diverges to negative infinity or something else. Yeah. So it's interesting that this other function, I'm going to try and draw these so they're close to each other. It's interesting that this other function, 1 over x squared, which looks similar to 1 over x, has a finite amount of area. It's small enough, or gets small fast enough, that that area is finite. So here we have infinite area. Here we have finite area.
Say that it's equal to 1.
Yeah.
Equal or close to 1?
The words that we would use would be that the area converges to 1. But it is totally correct to say that this integral, the integral from 1 to infinity of 1 over x squared dx, it is perfectly valid to say that that integral is equal to 1. Now, when you write this, what you actually mean is you've taken the limit and you found that the limit of it converges to 1. But we all agree that that is what that means. Other questions? So there's some more examples. Sure. So here's a classic example. Yeah, let's do that. So let's say we have, sorry, one second. The integral from negative infinity to infinity of x e to the negative x squared. Okay, so first off, I have 2 problem points. Negative infinity and infinity are both problems. Now here's the thing about definite integrals. The definite integral can only deal with 1 problem at a time. So if a definite integral has 2 problems, you have to break it up into multiple integrals. So I need to break this up. We're going to break it up. The integral from, pick any point between negative infinity and infinity. The classic usual choice is 0, but actually any value is fine. You can pick 1, -1, 3, 1,000. It doesn't actually matter. But the usual normal choice is to pick 0. So I'm breaking it up as the integral from negative infinity to 0 of x e to the negative x squared dx plus the integral from 0 to infinity of x e to the negative x squared dx. And then we're going to write each of these as improper integrals. So the first one is going to be the limit as a approaches negative infinity of the integral from a to 0 of x e to the negative x squared dx. And then the second one is going to be the limit as b goes to infinity of the integral from 0 to b of x e to the negative x squared dx. And this is a great example of where we definitely should do what you were suggesting, right? We should do the indefinite integral off to the side, so we don't have to write all the limit with the limits of integration a bunch of times. So off to the side, let's do, okay, the integral of x e to the negative x squared dx is not too terrible. It's a quick u sub. So we're going to let u equal negative x squared. And our du is negative 2x dx. So negative 1/2 du is equal to x dx. So this is going to become the integral of negative 1/2 du, and then my e to the negative x squared is going to be e to the u. So that's just going to be negative 1/2 e to the u, which is negative 1/2 e to the negative x squared. Great. So that makes the rest of this not too terrible. So we can rewrite this now as the limit as a goes to minus infinity of the integral of this, which is negative 1/2 e to the negative x squared, from a to 0, plus the limit as b goes to infinity of, again, -1/2 e to the negative x squared from 0 to b. And here's the thing that's true about these integrals here. If you break it up into multiple pieces, if one of the pieces diverges, you're done. The whole thing diverges. So actually, since I knew it was going to happen, I did both of them. But you could say, James, it looks like you're doing too much work, because what you should have really done is done one of them first, and then if it converged, then done the other one. Because if one of them diverges, stop. The whole thing diverges. Doesn't matter if the other one, doesn't matter if one of them is infinity and one of them is negative infinity. Infinity plus negative infinity, it's indeterminate. We can't say anything about it. Yeah, well, the thing is here, I know I need to do both of them because they're both going to converge. But if one of them was going to diverge, I would try and do that one first and then stop. But yes, you can totally, if one part of an integral diverges, if you've broken up into multiple integrals, you can stop there. The whole thing is divergent. The only exception to that would be if someone asked how it diverged, because then you would need to know what both pieces did to say, oh, it diverges to infinity, or it diverges to negative infinity, or we can't actually tell because one piece is infinity and one piece is negative infinity. So yeah. So let's see here. This is going to equal, so if I plug in 0, I'm going to get the limit. A goes to negative infinity. -1/2 times e to the 0 is just -1/2. Minus, if I plug in a, I'm going to get -1/2 e to the negative a squared. And then same deal over here. Limit is b goes to infinity. I'm going to get, if I plug in b, -1/2 e to the negative b squared. Minus, if I plug in 0, -1/2 times e to the 0, which is 1. And this is where I start to get, I feel like things are a little challenging. I mean, okay, the whole thing is a little challenging, right? But here's where I'm like, okay, well, what's happening? So if a goes to negative infinity, a squared, well, negative infinity squared is positive infinity, but then it's a negative of that. So it's e to the negative infinity. So what happens to e to the negative infinity? Is that something that's getting really, really large or really, really not large? You're looking at your wrong hand. It's the right hand. I know it's hard because you're like, most of us are right handed, so we're like, oh, no. So if you look at e to the negative infinity, it goes to 0. That's a great way of doing it. I always struggle with that. But you can totally think of the graph, right? The graph of e to the x does this. And so if you're going off to infinity, e to the x gets really, really large. But if you're going towards negative infinity, e to the x gets really, really close to 0. So e to the negative infinity is equal to 0. Here's what I prefer to do personally. I like to rewrite this as, I'm going to write this as 1/2 times 1 over e to the a squared. Same deal over here. I have -1/2 times 1 over e to the b squared. Because now a is going to minus infinity. A squared is still infinitely large, right? But e to the infinity, for some reason, it's easier for my brain to be like, oh, I know that e to the infinity is really, really big. Right? I'm just multiplying e by itself a lot of times. E times e times e times e times e times e is really, 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 really big. So this denominator is getting infinitely large. But again, just like in the previous problem, if your denominator is getting infinitely large, the whole fraction is getting closer and closer to 0. So this whole term here is going to 0 because the denominator is getting infinitely large. Same deal is true over here. If b is going to infinity, b squared is also going to infinity, and e to the infinity is getting super large. So this whole fraction and this whole term is going to 0.
You don't really think where it is. You just like think of like the function itself. Like where does e go to?
Right. Where does e? Mm-hmm. So typically, when you have e to a power, it's either going to go to infinity or it's going to go to 0. If the power is getting really big, it's going to go to infinity. If the power is getting really, really negatively big, it's going to go to 0. I personally have a hard time remembering the negative part, so I always like to rewrite it so that my power is getting positively large. So here, a squared is getting positively large, e to the a squared is getting really, really big. 1 over that's going to 0. Same deal here. So here I'm left with a negative 1/2 plus 0 plus a 0 plus 1/2, which ends up being 0. So the whole thing's 0? Yeah, the whole thing's 0, and here's why. If you were to graph this, here's what x e to the negative x squared looks like. Yeah, it's kind of like this. So x e to the negative x squared looks a little bit like this. Sure. My picture is not perfect, but the idea is, oh, look, this area over here, which is positive 1/2, is canceling out with this area over here, which is negative 1/2. So that's what's happening. That's why we're getting 0 there. Something to be aware of. And yes, I definitely should. Come on, pages. Time is it? Okay, got it. It's important to know. So the integral from negative infinity to infinity of x cubed. Question. Right, it converges. Well, it converges because it went to a finite number. So I wouldn't say specifically because it's 0, I'd say just because it's finite. But yes, you're right. I should have written somewhere on the bottom here, right? This integral, so our integral from negative infinity to infinity of x e to the negative x squared dx converges to 0. So what about this integral here? Well, this one is a problem. And now I've actually seen some math teachers teach this what I would call the wrong way. So every book I've ever read, every person I've ever talked to, colleagues, would tell you that this integral diverges. Here's why. We're going to break it up. And like I was saying last time, what you should actually do when you break an integral is then just treat each piece separately. So I'm going to deal with this piece first. So we'll deal with this piece first. If it diverges, we're done. The whole thing diverges. If it doesn't diverge, then we'll deal with this piece second. Doesn't matter which piece you do first, which one you do second. It only matters in that if you think one of them might diverge and the other one might converge, pick the one you think that diverges first, because then you'll be doing less work. So if there's any sort of indication that you think one is going to be divergent, pick that one. Here they're pretty much the same, so I'm just going to pick them up. So if I do this first one, the integral from 0 to infinity of x cubed dx is equal to the limit as b goes to infinity of the integral from 0 to b of x cubed dx. That's going to be the limit as b goes to infinity. The integral of x cubed is x to the 4th over 4, from 0 to b. That's going to be the limit as b goes to infinity of b to the 4th over 4 minus 0 to the 4th over 4. As b goes to infinity, what happens to b to the 4th? Right. So this is going to infinity, divided by 4, which is still infinity, which means this whole thing diverges. Now, I will point out, it is possible, although I doubt it, especially if your professor is Burke, there's no way she's going to, no, I know her, she's a rational person, she doesn't teach crazy math that's wrong, but I have seen professors teach this the wrong way. I've seen some people say, well, look, these areas cancel each other out. This area over here, right, this function looks like this. And so this area under this curve to the right, like this area over here, I've seen people say that those cancel out. That is incorrect as far as I have ever learned, ever been taught, ever taught people. So it is not okay to say that an odd function has an interval that's 0 if it's divergent. And there's actually a whole textbook problem, at least in one textbook I know, about how this is divergent. So definitely unless your teacher, you shouldn't because I know her. She's a good, wholesome math person. She knows the right. This should not be 0. So this definitely diverges. It is not equal to 0. But some people get on this whole kick about how, well, if I integrate an odd function from negative a to a, it's going to be 0. And it should be fine if those are infinity. Not true. Okay, that's enough of my soapboxing there. Yeah, let's do one more example of the other type of improper integral. We'll talk more about them on Thursday as well. So the other way a function can be improper is that it's undefined somewhere in the integral. Meaning, for example, if I like the integral from -2 to 1 of 1 over x squared, it's really easy to miss that this is improper, right? You could be like, oh, I know the integral of 1 over x squared. It's -1 over x from -2 to 1. That's going to be -1 over 1 minus -1 over 2. Oh, sorry, -1 over -2, apologies, which is going to be -1 minus 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 is -1/2, which is -3/2. It's totally wrong. If you look at the graph of this, well, first of all, how could it be negative if the function's always positive? 1 over x squared looks like this. So I'm calculating the area from -2 to +1, where I'm getting like all this here. Oh. I have a vertical asymptote. That's a problem. So I need to break this integral up into pieces so that my problem point, which is where it's undefined, is one of my limits of integration. So we're going to break this up as the integral from -2 to 0 of 1 over x squared plus the integral from 0 to 1 of 1 over x squared. And just like before, I would encourage you to do it one piece at a time, because maybe one of them is going to diverge. Let's look at this integral here. So let's look at the integral from 0 to 1 of 1 over x squared. So I'm going to write this as the limit as, what's the problem point? What are we actually, let's before we write the limit, we're going to do the integral from, is it going to be 0 to b or a to 1? Which one am I replacing? Right, I'm replacing 0, and you can use whatever letter. We usually use an a for the bottom and a b for the top. Okay, so then I want the limit as a approaches 0. Now, when people do this, they like to be specific. If I'm looking at this integral, right? If I'm looking at this one here, my a value is like there, and a is approaching 0. But specifically, a is approaching 0 from which side? Which side of 0 is a on? Is a on the right side of 0 or on the left side of 0? Right, so a is approaching 0 from the right. Just as a point to contrast this, if I was doing the other one, the integral from -2 to 0 of 1 over x squared dx, and I wrote it as the integral from -2 to b of 1 over x squared dx, I would say, oh, I'd have the limit as b approaches 0 from, well, b is like over here, b is approaching 0 from the left. People almost always do write that. So because it does actually make a difference sometimes. So be aware. So this top one, I'm going to get the antiderivative of 1 over x squared is -1 over, oh, I forgot to write the limit. Terrible, James. Do the limit as a approaches 0 from the right of -1 over x from a to 1. And then we're going to get the limit as a approaches 0 from the right of -1 over 1 minus -1 over a. Which equals, I'm going to, even though I would usually stop there, all right, limit as a goes to 0 of -1 plus 1 over a. So now, as a approaches 0, what happens to 1 over a? Undefined, right? Specifically, it's getting infinitely large. Positively infinitely large, because I'm approaching 0 from the right, not from the left. So I'm dividing 1 by a very, 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 very small positive number. It's like I'm doing 1 divided by 1/1,000,000th. And 1 divided by 1 over a billion is a billion. And a billion plus -1 is still very close to a billion. So this is specifically going to positive infinity. Which again, makes sense if you think about the picture we've drawn. The area under this curve definitely couldn't be negative infinity, right? It's all above the x-axis. So if it's going to diverge, it's definitely diverging to infinity. Again, not usually something we have to be specific about, but just in case you do, that's what I'm saying. So what, oh, sorry. And then what I would say here, great. So I don't even need to do the rest of this. This is enough to say, great, this diverges.